In this video, first I'm going to show you a little explanation behind the previous video, which is how to build an alcohol-powered speedboat, and how isopropyl alcohol and soap both interact with the surface tension of water and what surface tension is. And then after that, there's two activities. One where you make a paperclip float on the top of water, and the other you can make a penny with a huge dome of water on it, and you can see how many droplets you can get to fit on a penny. And you can see how soap affects both of those. Okay guys, look at these. These are water molecules. There's H2O, two hydrogens and one oxygen. And see how if you pull them apart, they kind of stretch towards each other? So they're all pulling to be together. Yeah, that's right. They're all pulling to be together. So if I have a soap boat like this, and I'm going to put it right here, and I have some scissors. Alec, could you get those scissors?
Uh-oh, what's going to happen?
Okay, so I want to ask you, if I cut the rubber band right over here, so they're all stretched out, right? They're all stretched out. If I cut the rubber band right here, which way is the boat going to go? Is it going to go that way, or is it going to go that way?
I don't know.
What do you think?
I think that way.
You think it's going to go that way? Let's see. I'm going to cut it. Which way is the boat going to go?
That way.
Let's see, and it does. It goes that way. But can we do it again?
Yes.
Well, we can't because it's broken.
Yeah.
But that's kind of like putting soap on it, because soap is going to break that surface tension. But once you break the surface tension, it's broken. But there is another thing you can do. Okay. In the previous video, we had a bunch of water molecules pulling on each other, and then we cut the tension between them with the soap, or the scissors in this case. This case, instead of cutting anything, we are adding something. This is a representative of a isopropyl alcohol molecule. Notice how it still pulls on the neighboring molecules, but the pull is much weaker, represented by these thinner rubber bands. These are wider, weaker rubber bands.
Yeah, like
so this
that's
time,
another way to break it. Only that's too hard.
So this time, instead of cutting anything, we're going to add this weaker, stretchier molecule, the isopropyl alcohol. So when I let my hand go, which way do you think this boat is going to go? Is it
that
way? That way or that way?
That way.
You think it's going to go that way? You think it's going to go that way? Well, let's see. We'll keep your eyes on the boat as I add this bigger, weaker tension isopropyl alcohol molecule. Watch the boat. See which way it goes. It went that way. And could I add another one of these to it and have it be even more that way?
Yeah,
we could. We can keep on adding isopropyl alcohol, and that's why I could keep on going and going and going with isopropyl alcohol. But if you cut it, like with soap, then you can't, because then the surface tension's just gone.
Yeah.
Here we can add isopropyl alcohol to this all day. So that's how it works with isopropyl alcohol. Here's an activity you can try, a challenge you can try. Can you get a paperclip, either a big one or a small one, resting on the top of water? Here we have some water, and you notice, as you can imagine, if I just put it on the top, it sinks down to the bottom. Well, there's a trick you can do to have it rest at the top, almost as if it's floating. It's not actually floating, that's when something has less density and rises up. This is caused by resting on the surface tension of the water, and there's a trick to doing it. If you want to do it without me telling you the trick, you can pause the video now, but see if you can get it to just stay there, resting on top of the water. So pause now if you want to figure it out on your own. Okay, here's the secret to getting a paperclip to rest on the top of water. So what you do is you get a piece of toilet paper, or even a tissue. Toilet paper works better. Get a little strip, cut a little strip, and then you're going to use that to let you gently place it on top of the water. Gently place this on top of the water. And hopefully the paper will absorb the water and you can kind of have it fall away. Now let me take this paper toilet paper out. Look. You can see the paperclip, which is mostly iron, which is definitely heavier than water, it should sink, but it is resting on the surface tension of the water. Now here's another experiment. I want you to try what would happen if you put a little bit of soap in this. Do you think it would still be able to float? What would happen if you put a little bit of soap in it? That's what I want you to try. Some animals use the surface tension of water to walk across it. You may have seen the basilisk lizard running on top of water. The basilisk lizard I just showed a clip of does not use surface tension to run on top of water. Instead, it just pushes and kicks the water away in order to propel it forward. If the basilisk lizard were to try to stand on water, it would just fall through. One animal that does use surface tension to walk on top of water is the water strider, and it can just sit there if it wants to. Another activity I want you to try is see how many drops you can get on a penny, one with soap on it and one without soap on it. So to do that, first you're going to have to make an eyedropper if you don't have one. Here's a very simple way to make an eyedropper if you don't have one. Get any straw, cut the bendy part off, and then you're going to fold it over, making sure it's nice and airtight on one side. And then all you do is just tape it off like that. It's nice and airtight on that side. And that's where you can pick up your water, give it a little squeeze, and then release it. Now this has some water in it, and you can do drop, 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 one drop at a time. Make it a simple water dropper. Now the challenge for this is how many drops of water can you get to go on the face of a penny without it spilling over. So there's my penny, and I'm going to just drop 1, 2, 3, 4, 5, 6, and I'm going to keep on going. I'm not going to tell you what number I'm at so far, because I don't want you to spoil it, how many I can get. I'm counting. Make sure you count when you do this so you can keep track. How many droplets of water are you able to get on your penny? Oh, looks like that topped out. I'm not going to tell you how many I got. I want you to see how many you can get. And then I want you to try the whole experiment again, but this time put a little drop of soap right on your penny and see how that affects how many drops of water will actually fit. The penny experiment, you could see that there was a big dome of water on top of the penny, and that's because all the water molecules were pulling on each other. You can see a much more extreme example of this in space. If you have free water in space, it forms a sphere of water. A lot of people erroneously think this is because gravity pulls it all together. Well, gravity does attract things together, but gravity is also very weak. In order to have any sort of meaningful, noticeable effect, you have to take the gravity of a whole planet, something like that. So even though there is gravity pulling things together in space, that's not why water forms a sphere in space. It's because the water's surface tension is pulling it together. And the last thing I'm going to show you is a little clip of exactly that. The surface tension of water in space on the International Space Station, pulling it in the shape of a sphere. And again, this is all caused by surface tension.